All right. Changing orientation and induced EMF, shortest section of the notes ever. An electric generator consists of a set of coils that have a radius of 0.05 meters situated between two strong magnets. The magnets have an approximately uniform magnetic field between them of zero point 0.1 teslas, and they can be rotated. Suppose that the electric generator creates alternating current with frequency 60 hertz and peak voltage of 150 volts. Okay, a couple of important things to note here: frequency and voltage. Okay, we haven't used frequency in a while, but frequency, right, if you remember from physics 1 with circular motion, frequency is that a full rotation, okay, occurs, in the context of this problem, a full rotation occurs 60 times each second, okay? So what's happening, okay, is that a full rotation of the magnets occurs 60 times each second. Now, one thing that's important to note is that when the magnets are vertical like this, okay, the magnetic field, okay, is going to, I'm going to draw it in a light color so I don't mess anything up here. The magnetic field is just going to go straight from one magnet to the next, right? It's all there. The magnetic field, when they're vertical, okay, flux, okay, when they're vertical is just NBA. Okay, because you actually wouldn't need to worry. The area vector would be parallel to the magnetic field, and so you wouldn't really need to worry about any cosine, sine, whatever. Okay. However, sorry, you wouldn't need to be worried about that cosine theta, right? Okay. Then, however, when they rotate, right, there's a point where they rotate and they're going to look like this. Okay. Okay, and when they rotate like this, okay, what's going to happen is now the magnetic field lines are going, this way, okay, and they actually are going to be perpendicular with the area vector, okay. And so when the magnets are rotated this way, they'll be perpendicular, which means that cosine theta actually resolves out to 0. So then the flux when they're side by side is actually going to be 0. Okay. So what you're going to notice is that it starts out NBA 0, NBA 0, NBA 0, right? Do you notice how it's going from NBA to 0? So that's actually our change in flux, right? So let's start out with our EMF equation, okay? With Faraday's law, delta flux over delta time, okay? We already just found out our delta flux, right? Our delta flux is that we're going from NBA to 0 to NBA to 0. So the change in flux is actually NBA minus 0, and it would just be NBA, okay? Because it goes from NBA to 0. Right? The range is from NBA to 0, okay? I'm saying that so much, okay? That's our change in flux, right? Okay? Now we need to figure out our change in time. We don't know how to figure out the change in time, right? Well, the change in time, right? How frequently does it go from NBA to 0? Notice that it only goes from NBA to 0 every fourth of a rotation, right? Notice that it only goes from NBA to 0 every fourth of a rotation. So if we knew how long it took to do one rotation, we could divide that by 4. Hey, how do we do that, right? How do we do that? You should remember from physics 1, right? That's the same thing as period, right? So it'd be 1/4 the period. Okay? And do you remember the relationship between frequency and period, right? Period, T, is equal to 1 over the frequency. Okay? Pretty straightforward. Okay? So that's going to be 1/4 the frequency, which is 1 over 60. Okay. So now I'm going to plug all of this in to the equation. Okay. Epsilon is equal to NBA over 1/4 times 1/60. Okay. Okay. We need to get the number of turns, right? It says the number of loops. So we need to get the number of turns. So we need to get n by itself, okay? So here's what I'm going to do, okay? I'm going to divide n on both sides, okay? That gives me epsilon over n equals BA over 1/4 times 1/60, okay? Flip both sides. That gives you n over epsilon equals 1/4 times 1/60 over BA. Okay. Then times epsilon on both sides, multiply epsilon on both sides, you get n equals epsilon 1/4 1/60th over BA. Okay? And then you just solve everything out. You just plug it in. Epsilon in this case, okay, epsilon is going to be this 150 right here. Okay? That's going to be our epsilon that we're going to use because that's the highest amount of voltage. That's when that's when the flux is equal to NBA. Okay? So we're just going to plug, and then B and A, I believe it gives it to us. B field is, yeah, point 1, and A, the area, we can math that out from the radius, right? So here's what we're going to do. We're going to do N equals 1/4. I just shuffled around the variables on accident. I didn't mean to write those first. I was just kind of on autopilot. 150, and then over B, which is 0.1, okay, and then the area is 0.05, okay, squared times pi, okay, so it's just pi r squared, right? Okay, and you would plug that into your calculator to actually get your value, and I got about 795.77 loops. I think you would round that up to 796 though, just because you don't really want to have a half loop or anything like that. Okay, that's it for that section. It's super short, and the next section is also really short too. Okay, so have fun.